or glucose as a substrate. What determines the fuel mix of a mitochondria? We haven't talked about that at all. So after we're done here, there's like 5 more lectures that sort of begin to talk about whole body exercise and how do these 5 systems we've talked about work in concert to keep the ATP level from dropping, and how do they, if you will, cooperate to get the job done. Okay? That was the ATP synthase. We talked about metabolic efficiency of glucose as the amount of energy that we can get into ATP versus the total enthalpy of the molecule. We get about 35%, which is favorable. That's your Prius probably barely does that well. So it's quite good. It's just that's a repeat slide. Okay, so talk a little bit of detail here, and I didn't pack today's lecture. I think it's relaxed. So just want to remind you, occasionally here, like I said, someday I'm going to bleed to death in my gym because I bite my tongue so hard when the trainers who are not UCD level students are saying things. Look, this is how it is. If you eat protein, you won't get fat. I've heard people say that. Can carbon-carbon chains in protein be the basis for fat synthesis? Good, let's follow the lines. There's an arrow. There's an amino acid going to acetyl-CoA. If this is in excess of the needs to regenerate ATP, you will indeed synthesize fatty acid from the protein after deaminating it. So you'll have stinky urine and make fat. Eat too much. I've seen people gain weight on high-protein diets because they weren't paying attention to total calorie balance. The same is true of glucose. Excess glucose can contribute to fat synthesis. Notice that fat is it's stored calories and only can contribute to acetyl-CoA. It's pretty much one way in terms of total energy flow, except for the tiny amount of energy in a glycerol could conceivably be used to make any glucose through gluconeogenesis. That would be extraordinarily rare. The vast majority of the energy in the fats is destined for energy synthesis, and you can't make protein nor make glucose from it. So fat is our committed storage form of energy. Okay. What else am I supposed to say about that? Anyone here remember the term anaplerotic factor? Probably should write that on the board because it's a complex Greek. Oh, this is heavy. Anaplerotic. This is a complex Greek-derived term. It basically means refilling the porridge pot. In the old days, there was always a big pot simmering over the fireplace, and you tended to throw things into it. It was always porridge, and so occasionally you put a handful of oatmeal, you throw another potato in, and just to sort of keep the pot turning. So anaplerotic factors refers to, if you go in here, there's a lot of little 4 and 3 carbon fragments, oxaloacetic acetate, OAA, and if you citrate synthase, but then when it breaks up, there's a lot of little fragments. Almost all of these fragments are not derived from acetyl-CoA. They're 3 and 4 carbon fragments, so they're coming from amino acids and from glucose. With me? And so we often, has anyone ever heard the saying, fat burns in the flame of carbohydrate? No. Very good. I can be useful to you, even though I'm not a biochemist. I can. So, a point that has to do with because fat cannot be a interesting. I should blank out when I tell it to you. Huh. Well, I'm not going to fight that. I'm going to do a little demo for you that's worth knowing about. So, in other words, because the anaplerotic factors, the basic intermediates in the TCA cycle are primarily derived from carbohydrate and protein. This means that fat, a lot of you have been asking me about keto diets. And the most common question you ask me is, what do I think about keto diets? You haven't asked me a question that's useful yet. You have to say, what do you think about keto diets for body fat loss? What do you think about keto diets with a calorie restriction? What do you think about a keto diet that's eating all the calories you need? These are all different things. What do you think about a keto diet for developing supermitochondria that are completely independent of carbohydrate? In almost all cases, none of these things matter, unless you're an Olympic athlete. Are you ready? Are you guys familiar with candles? It's an old technology for making light. It's different than using your smartphone. Now, what is the wax made of? In a candle. What is, oh, I just said it out loud, that was bad. What is this part? Wax, which is a form of fat, right? What is the wick made of? It's carbohydrate. It's cellulose. It's not a form of carbohydrate. We don't eat the candle wicks, but it's carbohydrate. So, I'm now going to do this as a visual metaphor of how mitochondria behave. You ready? I'm going to light the fat. Be careful. Well, that's really disappointing. This is the dumbest demo ever. Light! Now, what happens if I light the carbohydrate first? This works. The carbohydrate will sometimes dim just a bit before it melts. Nope, it's going to go. Okay. Ah! Are you tracking this? And most of that is oxidizing fat. It's fat that's burning within the lattice of the carbohydrate wick. Am I making sense? Okay, if it was the wick, it'd already be gone, be burned away. Okay, so fat is only burning in the presence of a very small number of carbohydrate calories. Now, if anyone is a physics major and explain why that is for a candle, I have no clue. But it happens to be exactly the way mitochondria are. My guess is that the combustion temperature of wax is higher than what the match provides. But if you light a wick, it probably gets as high as the combustion, and by acting almost like a carburetor, it's pulling up smaller wax molecules at high temperature and they ignite. That's my guess. You agree with that? Good. So, fat burns in the flame of carbohydrate, and thus I will, if you guys will ask me specific questions about keto diets, I'll try to tell you, but it's not in the content of this course, so I'm going to keep going. I will say that if you deprive if you take out of the diet the anaplerotic factors that cause this to turn, it will not turn as fast, and ultimately it'll slow way down. So, the one thing I will say about all forms of keto diet is if you stay on them 3 days, your work capacity drops like crazy. And so we have to start asking, why are you doing this? If your goal was to run a record-breaking half marathon on the 3rd day, you're doing it wrong. It's not going to happen. Okay? What else can I say? I will move on. It's just a big overview slide. Glycolysis, fat burns, transaminases, that's pretty good. That's all you need to know for now. So on to how it worked. So today what we talk about is, that was sort of an overview of where we've been and where we're going. Now we're going to talk about the use of fat in the mitochondria as a fuel source. So the first topic, and you'll see there's a lot of analogies to the way carbohydrate is used. It's not the same, but there's a prep step called beta oxidation. There's a breakdown in storage form. The glycogen is broken down by glycogenolysis. All right, glycogen phosphorylase. Well, fatty triglycerides are broken down by lipolysis, the breaking down of the storage form of fat, to glycerol and 3 free fatty acids. 3 free fatty acids, by hormone-sensitive lipids. Most of the fat we use on a daily basis is in our bloodstream, free fatty acids. and is removed at the level of the tissue. Once you pull that fat into the tissue, there is a fatty acid activation that occurs at the outer mitochondrial membrane, so there's an investment step of 2 high-energy phosphates. And then there's a prep step. These two talks about the fatty acid is then pulled into the mitochondrial inner membrane by carnitine palmitoyl transferase. I always like to call this carnitine acyl transferase. How many people have heard that? Yeah. Palmitoyl implies that a carbon is always 18 carbons long, and that's not true. So this is, besides being misspelled, it's misleading. So I like acyl. Acyl just means a fat chain of any length, because they can be as short as 8 or 6. Carnitine palmitoyl transferase, plus I like saying CAT. It's easier to say CAT in CPT. This is the rate-limiting step, is actually getting the activated fatty acid across the inner mitochondrial membrane to go to town on it. Then our preparatory step is to cleave this very long-chain fatty acid. If it was 18 here, we would have to take it through beta oxidation to cleave off 2 carbon fragments and attach them to an attach them to a CoA. And so we want 2 carbon acetyl-CoAs, because that's what can actually go into the protein. Is that all? This is all just fats arrive in a more reduced state. Remember, your typical fat is a chain of carbons with 2 hydrogens on each side, so there's very little resident oxygen on the molecule when it arrives, and therefore you need to use more oxygen to oxidize the fat. Fat oxidation derives huge amounts of ATP, but the enzyme chain is much, much longer. Plus, you're importing the vast majority of this through the bloodstream. So not only do you have at least a 10 times longer enzyme chain when you add it all up, you also have whatever the time cost is of moving the fat from the fat cells to the tissue, and that's seconds. Remember, seconds in enzymatic time is like eons. So fat is quite slow in providing ATP, but it's almost infinite in terms of how much total ATP you could get from the bodies you have now. Most of you are carrying at least a month and more like 6 weeks of fat. If we gave you vitamins and water and just put you on starvation, you would last a long time. So, where is lipid? Since I've just referred to your lipid stores and you're now deeply offended that I've called you all fat. Remember, glycerol is kind of a 3-carbon chain alcohol. This thing is a good fuel source, but in our bodies it's not. You can actually get refined glycerol and drink it. It has some performance benefits for endurance work, but it's just a minor player. What it's really used for in fatty acids is you make an ester bond between a long aliphatic chain of free fatty acid and this, and you get a triglyceride. There's the backbone of glycerol, and here are the chains coming off in right? And that's how it's stored. That process is fat synthesis done inside the lipid or adipose cell. There are small amounts, you can see by these lines here, that this must be muscle cell, and there are small amounts of intramuscular lipid. I presume this is triglyceride, but there's not much of it. There's a bit of it. Anyone notice, since Thanksgiving is coming up, that the breast meat is usually somewhat drier than the dark meat on the legs? The reason you notice that, you also notice the dark meat is dark, and it's a little more oily, which is why I like it. The dark meat is dark because it has more myoglobin, implying that those cells depend more on oxygen transport. And the oil content is higher because there is more intramuscular triglyceride in slow twitch fiber, which is what the leg muscles, the dark meat is slow twitch fiber. And we'll talk about fiber type this week. Okay? When you look at, here's one of these little webs showing you, so most of, after a meal, fat moves into the bloodstream as chylomicron from the GI tract, and so the GI tract should also be on here. And that would be the straight absorption of triglycerides. There might be some free fatty acid in your food. Usually, if you're talking about someone who's postprandial, who has not eaten recently, the fat will undergo lipolysis in the fat cell, releases its free or non-esterified fatty acids, free fatty acid or NEFA, non-esterified fatty acid. These, just like oil, are not that water soluble. They just have a single carboxylic acid end, but they can be, by fixing that carboxylic end, not covalently, but emulsified by a protein like albumin, you can get this stuff to go through the bloodstream without forming micelles. So most of the free fatty acids travel bound to albumin, reversibly bound to albumin. What else does this show? Fat uptake in the muscle. Whenever we're unfed, that tends to be fat. Fat tends to be our basic substrate for all forms of metabolism except the brain. And we'll talk a little bit more about the way in which glycerol backbones and other small 3-carbon fragments can be synthesized into fresh glucose, gluconeogenesis. Again, that really is something that only happens in deep starvation or exercise beyond 3 hours. Okay? So for the next step, let's just talk about this lipolysis in detail. And then we'll get it to the muscle cell in a couple of slides. So here's adipose tissue. I wish they wouldn't call it hormone-sensitive lipase. Does anyone know what hormone it is? Because it's 2 very specific hormones. Catecholamines. They ought to call it epinephrine-sensitive or catecholamine-sensitive lipase. Because the primary stimulus, I guess cortisol may do some of the hormones, and maybe that's why they don't call it catecholamine-sensitive. I'm just an exercise guy, so I don't think about starvation that much. So certainly, epinephrine and norepinephrine, epinephrine primarily, activates this hormone-sensitive lipase, and what this lipase does inside the adipose tissue is to cleave this glycerol backbone, break those ester bonds, and release 3 non-esterified fatty acids plus the glycerol into the bloodstream. This figure's a little bit more general, because it's showing here's a meal, small intestine. There's a triglyceride taken up as a chylomicron into the bloodstream. But if we're talking about postprandial, most of the fat in the bloodstream is coming from adipose tissue or lipoproteins released by the liver. Now this is showing, and I have to say, adipose lipoprotein lipase, muscle lipoprotein lipase. So these are showing enzymes that are associated with the wall of the capillary and are either removing, in the case of muscle lipoprotein lipase, they're actually breaking down. If this is carried in a complex form, you have to break this down to directly enter it. I have to say that this is a tremendously minor pathway. The vast majority of your fatty acids that enter the muscle are entering as fatty acids. And so let's go to that step. And I'm not here to teach you about eating, and I'm not here to teach you about lipoprotein in the bloodstream, although that's important, and we'll talk about it in 117 in the spring. So here's hormone-sensitive lipase. I guess we have one more step before we talk about receiving. Oh, there's why it's called hormone. So insulin inhibits it. So it's sensitive to insulin as well as the catecholamines. The catecholamines, notice once again, we have protein kinases that are activating it or unactivating it. So it's very analogous to glycogen phosphorylase, which the target of regulation was actually its regulatory kinase and phosphatase, not the enzyme itself. So it's analogous to that. What the hormones are doing is activating the protein kinase to put a high-energy phosphate on the actual hormone-sensitive lipase, and this phosphorylated form is the active form that deesterifies at a high rate. Is this all right? So this is how you flood the bloodstream, have a lot of epinephrine. Then when the free fatty acid, again, reversibly emulsified by albumin and other blood proteins, arrives at the boundary of the cell, here's the fatty acid coming off, fatty acid binding protein, it's all written down here to read this, but the fatty acid binding protein grabs it and immediately passes it onto a translocase called fatty acid translocase, which abbreviates to fat. This translocase is often subendothelial, let me try again, is often subsarcolemmal in a muscle tissue. And the vesicle will upregulate into the boundary when energy state drops, such as in resting starvation or intense exercise, and it responds to calcium as well. So contraction stimuli upregulate the transport protein for fats. What does that remind you of? What other receptor? Doesn't that sound like GLUT4? So there's a lot of little analogies. Don't take it as just absolutely the same, but there's a lot of little analogies that will help your memory. Okay? Yes, ma'am?
In the previous slide, why did you have epinephrine and norepinephrine as a positive and?
Yeah, I don't understand that, to be quite honest, why they put both. Norepinephrine is going to be less powerful at activating than epinephrine, but they both will activate lipolysis. Yeah. I didn't understand that either. Remember, a lot of times you're getting these from biochemistry texts, and it's hard sometimes. People don't make very good slides, to be quite honest. They don't make good figures. I try to redraw the figures more. So, once the fatty acid, so we get the fatty acid into the cytosol of the cell, a second solubilized, non-membrane associated fatty acid binding protein in the cytosol begins to take this, and where must we ultimately get that fatty acid before we can get anything done with it? What's the target organelle? It's got to get to the mitochondria. So let's do that, because that's where the business end. Once we get it there, and again, realize all the steps I just named take a long time relative to enzyme reaction rates. So fat's going to be a slower fuel, but boy, do you have a lot of it. So this carnitine acyl or palmitoyl, that's how it's spelled, transferase, is actually two different enzymes, one on the outer, or two different proteins, one on the outer membrane of mitochondria, one on the inner, but they work together and they're referred to as a single moiety. The activation step for this fatty acid is to, just like with glucose, when it enters the cell, the way we use hexokinase to trap it behind the membrane, here the fatty acid comes in from the cytosol, and by taking one ATP all the way down to its lowest energy state, this is a very rare reaction. And remember I told you that AMP just carries hella information in terms of letting the mitochondria know about energy state. And so it's very interesting that when this happens, it's warning the rest of the mitochondria, we're about to up our synthesis of ATP. And so here's our fatty acyl CoA. It attaches a CoA to it and is in the active form. Then a carrier protein called carnitine carries that activated, I can make words, breaks off the CoA, binds to the free fatty acid. The free fatty acid then moves in through a translocase in the inner membrane. Remember, this is the one that's hard to get across. The carnitine comes in, and the carnitine palmitoyl or acyl transferase 2 gets it to a fatty acid CoA. I don't think you need to know all those steps. Okay, don't memorize all of this. Memorize that it takes 2 high-energy phosphates to get the thing into the mitochondria. Carnitine, I just have to pause for a moment about the way people are, a little bit of knowledge can make you do dumb things. Carnitine is sold at GNC. You can buy a bottle of it, and their recommendation is you put it in your mouth and swallow it, and this will somehow increase fat oxidation. Where would the carnitine have to get in order to do that? To your mitochondria inside a cell. I drew this is the molecular structure of carnitine. 4 carbons plus a nitrogen with 3 methyls on it. The likelihood that this actually makes it into your bloodstream out of your GI tract, it would astound me if it does. And once it gets in if it were to get in the bloodstream, that it would actually get to the target tissue and then penetrate to the mitochondria. I am deeply doubtful. Just thought I'd point these things out. Putting stuff in your mouth is a very primitive delivery system. It's great for food, by the way. But if you're hoping to, I'm going to eat whole mitochondria. What else do you need to know about this? Oh, by the way, if you were to amp up your carnitine without actually increasing your carnitine acetyltransferase, would that be useful? No, you'd have to change them in tandem. And this is an enzyme, which I guarantee you cannot be eaten. Enzymes are always destroyed by the stomach acid. So the best way to do this is nature's way, which has to do with contractions. You'll see, you can certainly increase your carnitine and CPT content. It's just you have to do it with exercise. So here's the prep step. The equivalent of cytosolic glycolysis for fat oxidation is to, in the inner membrane, cut the long fatty acid into little 2-carbon CoAs. This is useful to the TCA cycle. So I believe what's done here, they don't tell me what R equals, but if it was palmitic acid, it would be 18, I believe. And so what happens is you go through these steps, and I want to remind you, anytime we cleave a high energy bond between carbon and carbon, or here between carbon and the sulfonyl CoA, you're going to tend to release energy. So notice here, you dehydrogenate, oh, that's going to be a cleavage of carbon, and so immediately you get an FADH. There's a water going on at a new place. Here is NADH, and notice 1, 2, 3, 4. Wait, 1, 2, 3. Where's the energy coming from? Anyone see it? These things are becoming clear to these molecules are becoming more oxidized because you're producing reduced cofactors. At some point, you're going to start to actually break these into fragments. So here's the first round, starting with a C16. What is C16? Stearic acid? Is that right? You guys want me to remember an awful lot of stuff. So C16, after one round of this, you drop down to an acetyl-CoA plus a 14-carbon fragment. You do it again. Go 14 down to 12, another CoA. 12 to 10, another CoA. Am I making sense about how this works? Now remember, when you get to your last round, you're going to have a 4-carbon fragment. How many more times do you have to go through beta oxidation with a 4-carbon fragment? Just once. Live long and prosper with your 2 acetyl-CoAs. So remember that the last round of the beta oxidation will liberate 2 acetyl-CoAs from a single pass. And so the amount of CoA you get from a fatty acid chain is going to be the number of carbons divided by 2. So if it's stearic acid with a C equals 16, you're going to get 8 CoAs out of it. The number of passes through beta oxidation, the number of times you have to go through these steps, is going to be N divided by 2 minus 1, because the last step creates 2 acetyl-CoAs from a 4-carbon fragment. Notice that each step in beta, each reduction leads to 1 NADH and 1 FADH2. So how much ATP could you redeem these for in the deep mitochondria, in the electron transport chain? 1.5 and 2.5 equals 4 ATP. And that's before you've even hit the TCA cycle. So here's a summary of what we just said. There's your activation step. You have to subtract that off at the end. You get an FADH and an NADH for each pass. You repeat it. The number of carbons, so 18 for palmitic acid, 18 divided by 2 would be you get 9 acetyl-CoAs, and in 8 passes through beta oxidation. Is this all familiar? Vaguely, you've heard this before. Okay. So let's do one and do the actual counting. So we have negative 2 ATP to take off at the end. C16, how many acetyl-CoAs are we going to get out of C16? 8. And how many passes through beta oxidation will make it happen?
7.
7. So 7 at 4 ATPs a pass is going to give us 28 ATPs just for the prepping, just for the chopping of the molecule into acetyl-CoAs. Before you've even started TCA cycle, you get 28. Now then, you have 8 acetyl-CoAs. How much ATP equivalent do you get going once around the TCA cycle for an acetyl-CoA? 10, right? And so 8 passes, 8 acetyl-CoAs are going to give you something like 80. Well, this is 108. You have to remember to subtract our investment step of 2. So you're going to get 106 ATPs out of a single carbon-18 palmitic acid. So you're going to mean about a huge amount of energy compared to what you get for glucose 30. I went ahead and counted all the enzymatic steps because apparently I have no social life. And if you actually count the number of enzymatic steps in that, you get something like, and assuming that the enzyme time spent on a reduced cofactor being changed into ATP in the electron transport system, it comes out that if cytosolic glycolysis has 10 steps, basically once you get to G6P, 10 steps, there are 220 enzymatic steps to actually get to ATP in beta oxidation. So you see that it's slower. It's immensely slower, although it gives you a huge amount of energy. So compare rest to most intense exercise. What are fats going to be the best suited for given the rate of living? Resting. Fats rock for resting metabolism, and indeed they are our default fuel when we're at rest. What's going to be a better fuel for the highest intensity exercise where you're just in a big giddy up hurry? Carbohydrate. And you'll see, we'll develop that idea through 3 more lectures after your midterm. But you can sort of see the writing on the wall coming just from the way these are laid out. Okay, let's think about, next step would be, let's think about the metabolic efficiency. In other words, the fat molecule has a certain total amount of energy in its carbon-carbon bonds. We could call it the enthalpy. How much of that do we harvest? We know it's going to be the minority because entropy always wins. But what do you think the efficiency is? Because now that we have these numbers, we can do a calculation. That's the total enthalpy of a 18 palmitic acid. This is how much goes into ATP, and look at that, isn't that? Wow. Wow. Kind of makes you think that might be the higher end, because it's exactly the same for the carbohydrate. It makes you suspicious that there's been a heavy evolutionary selection and you're approaching the limits of what a biological system can do in harvesting energy, because they're the same. Very different substrates, but the same. Does that all make sense? Okay. I'm so pleased. So I still have about 4 slides to go, and they're very different. I'm going to sort of change speeds. So this is metabolic efficiency. Efficiency is always a ratio of what I was trying to get versus the whole. So I want to, you guys are grown up enough now that I can talk to you about work efficiency, which is, when we talk about efficiency, almost always you're talking about work efficiency. So here's a human work efficiency. You can derive work efficiency from this information. Here's oxygen consumption in steady state. Resting oxygen consumption is 1/4 of a liter, so resting oxygen consumption would be down here. These are workloads starting from about 20%, oh sorry, that's about 30% of VO2 max, going up to about 90% of VO2 max. This is the actual workload. By the way, what is the single biggest thing you notice? It's pretty linear. And do we see a lot of R's greater than 0.99 in biology? Yeah, this is biophysics, folks. If you want to make this amount of work with an organism of a fixed efficiency, the more work you do, the more oxygen you must consume to run it. It's biophysics. Okay? So now I'm going to actually do the efficiency calculation The efficiency is going to be something, since this is the total energy release, and this is the external work done. They have to be in the same units. Right now, this is in oxygen, and this is in kilopound meters per minute, which is a watt equivalent. So it's going to be the reciprocal of this slope is the efficiency. Don't freak about this, and I will not make you calculate it. But it comes out that you can convert, this red arrow is indicating a calibrating standard that was used in our lab for 30 years, which is put a human at 200 watts of work, and they will consume 2.6, 2.55 liters of oxygen, plus or minus. The plus or minus comes from basically how heavy is their leg. Dania swinging her small leg will consume less energy in internal work than Greg swinging his giant leg. But that's the only source of variation. The external work efficiencies tend to be very constant. So 200 watts, I was able to convert this to about 900 joules per second. So if you take 200 divided by roughly 900, you get a gross work efficiency of about 22%. If you're very careful, what you can do is you have the subject do zero load cycling, where all they do is move their legs at the same speed as the work, measure what that does to their energy consumption, subtract that off the total, and you get what's called a net efficiency. This is what's published in most research, and that comes out at 27. But again, our human efficiencies are roughly 25%. That okay? That's work efficiency. Oh, I was going to make a contrast. So realize that that oxygen consumption includes, this number is just to get to the ATP. So from the free fatty acid, you're dropping down to about 35% just to get the ATP. Now notice, I've just told you it goes from 35 to 25% when you then take that ATP and do external work with it, express work with it. Well, that's a 10% drop. What it implies is once you have the ATP, about 70% of the energy in that tertiary phosphate is captured in the resetting of the myosin head, which is astounding. The implication that there's only another, there's a drop off of just 10% between metabolic efficiency and work efficiency implies that the energy harvesting by the myosin head is incredibly high efficiency. That all okay? I told you that among my many myths that you encounter when you talk to people, say, oh, I'm so much more efficient now that I'm in shape. And I understand what they're trying to say. They're trying to say they're a lot gooder. And it would be better if they just said gooder. Because when they say efficiency, they're saying something highly specific. The proper way to say it is, I am so much more capacious now that I'm in shape. You have a larger capacity. It's not the efficiency. So this leads to arguments when we go to national meetings, the American College of Sports Medicine, people who worry about these things. So is efficiency an adaptable function? Well, I just showed you that metabolic efficiency, there's not a lot of wiggle room there. That's been heavily selected for a really long time. Work efficiency, yeah, it's actually reported. And so I have to explain this graph. Does efficiency change with training? Yeah, there are reports where the best one is probably when Lance Armstrong was measured in Chester Kyle's lab, and they measured him again a decade later when he was starting to really win a lot more. And they found that his efficiency had gone from 25, are you with me? Everyone listen, it's a big deal, to 26 and a half. Right? And everyone, I mean, I'm doing this because you really dance in the halls if you get a change like that. That's huge. First thing to know is that's on the measurement error of the noise in efficiency measurement. So it's barely detectable if it's real. The second is, how much does that matter for everyday Joes and Josephinas? Does it matter to be 1% more efficient than your competitor if you're in the Olympics? Well, yeah, that's probably first versus third. So efficiencies do change. It generally takes 3 to 5 years of intense, Olympic level training to make it happen. And it's the last thing that happens, and it's the smallest of all the changes. What most of you it's pretty easy to go from being an average individual, you adopt training, and get an immediate, within 3 months, 25% increase in your work capacity. That's a piece of cake. Your efficiency will not have changed at all. That's that little red line. The elite athlete tends to have a greater untrained max. That's self-selection. They're just born better with cardiovascular systems that are greater. They train and they get another bump in terms of adaptation, and then usually only if they are competing at high intensities among other elite athletes will you see this efficiency change, and it contributes about 1% to their total superiority. It's pretty small. I'm trying to be balanced, because you'll hear people say, oh, efficiency changes. It's like, against the backdrop of everything else, it's pretty small.
How do you find an untrained? Is that just when they're like off season?
It's usually when they're injured. Yeah, you do have to kind of, Songs is saying, when does an elite athlete stop training? And the basic answer is when they're broken. Because you're right, it's hard to get them to stop training. Greg LeMond had a really good opportunity when he got married. He went out hunting with his father-in-law who shot him in the butt in a shotgun accident. So Greg LeMond had a 1-year period where his butt was healing. He was tested in our lab. He came back after complete detraining for a year, and he had a maximum of 64 mils, which is beyond what most of you would have in maximal aerobic training. So you can be bitter about that. We'll talk about it later. I think it's my last, 2 more. This is another kind of a ratio. This is not an efficiency, but it's called a phosphate oxygenation ratio. You'll hear of it, the P to O ratio. So for how much oxygen do you consume in order to create a certain amount of ATP? And this varies between our 2 substrates that the mitochondria uses. We're talking about oxygen, we're talking about mitochondria. So notice that glucose arrives partially oxidized. See that oxygen there? So it arrives partially oxidized. And so you get more ATP with less oxygen added because it's already partially oxidized. You can bounce its energy state up higher and have it fall apart quicker with less oxygen. With a saturated fatty acid, you have to get more oxygen on, see, it's arriving with 1 O2 on its, what do you call that thing? Carboxylic acid group. And so you have to add tons of oxygen to this before it falls apart. Now, I happen to think that this is actually almost irrelevant, but it is going to help you remember something. If you were in a situation where the availability of oxygen was becoming limiting, okay, since none of you are coal miners that get trapped in small boxes, can anyone tell me in your daily life when oxygen might become limiting? When you're working your ass off at maximum oxygen transport. Are you with me? That would be the only time that this PO ratio would start to be an issue. What would you choose to use if you were being limited by the amount of oxygen that you could get in? Which fuel? Glucose. And that turns out to be true. The harder you work, the more you shift towards glucose metabolism. I happen to think that the way this comes out is almost an accident. I don't really think it's a determinant, but it turns out to come out in the same direction that every other variable comes out, which is that carbohydrate is our prime fuel for high intensity work, whether it's anaerobic or aerobic. And that's worth remembering. Everyone okay so far? Everyone's head is on fire? Checking. Last slide. We'll get out a little early. Just as we leave this, I want to remind you, we leave this topic of the basic pathways. The area that this should differ the most, and I understand your biochemistry professors are pretty sharp, and they may have already told you this, but the role of calcium, as you go through and do your reviewing, you remember you've reached path and you're saying, what turns this off? What makes this go faster? Not every one of the enzymes that we're concerned with is sensitive to calcium, but a remarkable number of them are. So let's briefly do some of them. Calcium is released by the sarcoplasmic reticulum inside the working cell. Only the working cell does that. And that also allosterically activates glycogen phosphorylase, right? It presence of calcium upregulates the GLUT4 transporters. Today we learned another transporter gets upregulated with calcium. What's that? The fat transporter gets upregulated. It activates carnitine acetyl transferase. Calcium does. And by the way, this is the rate, if I didn't say it before, this is the rate limiting step in fatty acid oxidation, is how quickly you can get the fatty acids imported into the mitochondria. So having it be in short term stimulated by calcium and long term just add more total mitochondria, you increase your fat oxidation capacities. We saw before that calcium, well, it takes a little time to build up inside the matrix of the mitochondria to get in there, to diffuse in there. But once it builds up, it activates isocitrate dehydrogenase, which is the rate limiting step in the Krebs cycle. So this presence of calcium, and remember, calcium is anticipating the drop in ATP. When you start the contraction, ATP hasn't dropped yet. ATP drops if my nose is ATP. Remember, boom, boom. ATP, the first place it's used is to break that Raeger complex. And so all of this is a wonderful example of feed forward. Then, if you do have small increases in AMP or drops in ATP, what kind of feed is that to the enzymes? If that's allosterically detected, that's actual feedback. Okay, great, you're doing well based on the calcium, but we're still falling behind a little bit. Amp up that enzyme, drop that Km by a little bit more, and the enzyme will run perfectly. Does that make sense? All of this is how we match energy recreation to the rate of energy use. And that's your primary focus as you review getting ready for the midterm. Okay, I'll see you guys over in